Mr. Gallant.
And I'm Coach Parrish.
And we're here at Green Acres Middle School where we're doing 8th grade science, and the unit is Unit COVID-19.
Earth's place in the universe.
So let's talk about where we've kind of been so far. So Coach Parrish, what about lesson 1?
Our first lesson was our initial model, which we created from our anchoring phenomenon video, which showed us a time-lapse video that seemed to be everything moving around Earth, which we know is not 100% true, so we knew that this one was wrong, which led us to our next model.
In our next model, we started actually looking at how things moved across the night sky. What we came to find is that, okay, that the Earth is spinning in a counterclockwise motion, and that the Earth is spinning around the sun in a counterclockwise motion. So it's not everything moving around the sun, but or not everything moving around Earth, but it's everything moving around the sun. So from there, we started moving on.
And we know that the model we had for that one could have been right because it wouldn't give us all 4 of the seasons that we're supposed to have. So we know that we had to be offset a little bit, and we have to have our tilt, that 23.5 degree tilt on our axis. And we know that we move in this ellipse, and that when the northern hemisphere is pointed towards the sun, we're furthest away, but that's our summer. And we know that in the southern hemisphere, it's their winter. And we know that when we're close to the sun, we're tilted away, but that's our winter because we're tilted away, and that is the summer for the southern hemisphere. And here we have our 2 transitional points. From winter to summer would be spring for us, fall for them down there, and then from summer to winter would be fall for us and spring for the southern hemisphere.
And from there, we said, okay, well, how does light hit these different areas if there is a tilt? And what we started noticing is that because of that tilt, if it's winter or if it's summer for us and we're tilted towards the sun, then our North Pole would have sunlight for 24 hours, while our South Pole would have darkness for 24 hours. And it's the complete opposite on the other side. When we're tilted away, we have nighttime for 24 hours at the North Pole and daytime for 24 hours at the South Pole. And Coach Parrish, why is that?
It's because of the way that the rays hit Earth's surface with that tilt. Since we're not straight up and down, it's not going to be an equal amount up here and down there. So since it's tilted, when we're on that way, we're tilted, I believe, away. The North Pole isn't getting as much light rays or heat energy as it should, and the South Pole is. On this side, when we're tilted towards, the north part is getting a lot more heat energy or sun rays from the sun, and then the south is not.
Okay, so from there we started talking about the moon's phases as it goes around the Earth. And what we found is we always start off with a new moon, and after about 7 days, as the moon started getting brighter, what we call waxing, 7 days we have about the first quarter moon, another about 7 days we have the full moon where it's the brightest and the fullest, and then it starts getting dimmer as it goes back, and that's what we call waning. And it goes through gibbous, the third quarter, waning crescent, and back to a new moon. And that's about 28 days. And it's not that the moon is slowly losing more light or gaining more light. It's actually our perspective of the moon as it goes around the Earth. What we're able to see of the light that's hitting the moon. So when it's a new moon, half the moon still has light, but we're only able to see the dark side. When it's a full moon, the other half of the moon's dark, but we can only see the light that's full with light. And that leads us into our lesson 6 model, Coach Parrish.
Which was about the eclipse model. And we know that we talked about totals. We talked about a total solar eclipse is that the sun is being blocked. And this happens when the moon aligns straight in front of the sun. But remember, that's not for everybody. That's only at this certain spot that these people in this area or this place would see the total solar eclipse. Everything just around it would be a partial. If you're way out here, it'd just be a normal day for you. And then we talked about total lunar eclipse, which is the moon is being blocked by the Earth, which everyone on this side will definitely see that happen because the Earth's bigger than the moon. That's why. And
they don't happen every month because the moon has a 5-degree tilt.
Yes.
So it has to be the perfect situations for all this to happen.
Right place, right time.
So location.
Exactly.
So what we got into at the last part of the lesson is I asked you a question, Coach Parrish, and I said, why does the moon orbit around Earth? And I asked you, are they dating? And we had a couple of discussions, but we kind of left them with a little bit of a cliffhanger there.
We left them hanging.
We did. So that leads us into our next question, and that is, lesson 7, why do the Earth and Moon move this way? So let me ask you some questions, Coach Parrish.
Fire away.
So we just went over these models. What are some of the things that we know are moving in space?
Well, with our model, we know we've dealt with the moon, Earth, and we know there's a lot more. We just haven't covered it yet.
Okay, and with those things moving, what kind of events do we start having?
Well, we have daytime, we have nighttime, we have seasons, we have eclipses.
Okay? So, but here's the big question, Coach Parrish.
Okay.
Why is everything moving? Why is it not just sitting still? Why is the moon orbiting around the Earth? Why is the Earth orbiting around the sun? Why is everything we see moving?
That's a very good question.
You know what? We found a really cool video that explains this really awesomely. So why don't we get to that video right now?
The explanation for gravity is that matter bends space. And so you put mass in a place in space, it warps space-time, and objects are not feeling a force of gravity, they're just following the natural curvature. And so this is a sheet of Lycra. Where do you get this? This is my old bike shorts. Sale. And so you put matter, and it warps space-time. And so if I have another object, it also warps space-time. They feel that, and they're attracted to each other. And so that's Einstein's picture of gravity. Objects warp space-time, feel that curvature, and move accordingly. If you have more mass, it's going to bend space-time more. And so if you have objects here, they are going to respond to that, right? And so you put something there, now it's attracted. Now, in reality, that big mass would feel the warping of space-time by the marble too, right? It would move a little bit, but we usually ignore that. You know, the Earth makes the sun move a little bit, but it's so small you can ignore it. The moon makes the Earth kind of wobble around a point 3/4 of the way from the center of the Earth. We usually don't account for that when we're looking at satellite motion. Well, instead of just letting go of one, what if I give it a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations from other planets and things, but this one does lose energy and spirals in. If I don't push it as hard, it will do an ellipse for a while anyway. And let's get some more here. So one of the things I thought of to do with this is when you study the solar system, all the planets are going around the sun the same way. Why is that? Did God decide that he only liked clockwise, or depends on whether he's above or below the solar system, right? Why is everything going in the same direction? Well, the answer is it wasn't. Different directions. But there was a preferred direction. The disk it formed from had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way. That works 90% of the time. And so I have slightly more in one hand than another, but I don't consciously do that. And you want to get them so they spread out a little when you throw it.
It's because they're colliding with each other that you...
The ones going the wrong way get eliminated, right? Now there also would have been, this is where this analogy breaks down. There's, another dimension, right? But those things that were out of the plane also, that weren't near the preferred plane, also got eliminated. Some things we discovered using this, also had just some larger marbles, might as well put them out. But they bend space-time too, right? And so maybe, you can get one thing to orbit another. There we go.
Oh my God.
So the Earth-Moon system, maybe? Another thing this does, you've probably seen plastic ones of these, right? The Discovery Center, Children's Discovery Museum in San Jose has one. The Exploratorium has one. Sometimes they have them at shopping malls to get you to put money in it. But one thing you can't do with those is put two masses in. And so when we went to the moon, when we first started, we sent our spaceships on what are called free return trajectories. So they would go to the moon, this is hard to get to happen, and they would come back in like a figure eight. And so that lets you show, now of course the moon's a lot smaller, but if you look at the plots of the free return trajectory back from the Apollo program, you'll see it has a figure 8 sort of shape. And so this takes a little bit of practice to be able to do the figure 8s. These clamps around here, you can adjust it to make it tighter if it's not working. So Steve and I, when we set this up in the morning, we played around with it, and actually I think it was working better than it usually is.
Okay, so now I know what's on my list of things I need to get for my classroom, because that was really cool.
Yes.
So what we started to realize is we have some answers now. So what about objects makes gravity stronger, Coach Parrish?
Apparently their size.
So how big something is determines how much gravity it has. So if it's bigger, it has more gravity. If it's smaller, it has less gravity.
And by bigger, we mean more mass.
More mass.
matter.
Yeah, because we might weigh the same, but we're different sizes.
Correct.
It's about the mass. Okay, so let's create a model. So first of all, before we create any model, we have to figure out what we're going to use in our model. So Coach Parrish, let's make this an easy model. So
Sounds good to me.
How we represent each object?
Let's do circles.
Circles are easy. How will we represent gravity?
Well, we've done it before. Why not use arrows?
Yeah, arrows. We've done arrows. And then, but there's different amounts of gravity determining on its size. So what do we use?
Let's use size of arrows.
Size of arrows and size of gravity, amount of gravity. That works perfectly. So let's think. Okay, so first of all, we said circles.
Yep.
So if we're doing our circles out of the sun, the earth, and the moon, which object's the largest?
Oh, the sun, of course.
The sun, so it gets the biggest circle.
Correct.
Okay. Then we have the earth and the moon. What's the next biggest?
Earth.
Earth. And then finally the moon's the smallest out of the three here. So now we said, okay, we're going to represent gravity with arrows. So arrows are different sizes. So if we have the sun, the earth, and the moon, which object would have the most gravity?
Well, that would be the sun.
Why the sun?
It has more mass. It's bigger.
Okay, so it's going to get the biggest arrow. Then what?
Earth would be next.
Earth would be next. Now, does the moon have gravity?
Yes.
Because it's big, it has mass, so yes, the moon does have gravity. We might not think about it, and it's something in the next lesson we're going to prove that the moon has gravity. It's really, really cool. But, so we have kind of our very basic model here. But here's the thing. We know about gravity pulling on Earth. Why don't we just crash into the sun? Why are we going in a circle? We should be slowly getting closer and closer to the sun like we saw in that video. Those marbles got closer and closer to the weight. Why don't we get closer and closer to the sun?
Well, we do and then we don't. It would depend on, as you saw in the video, the marbles being thrown around. They had some force that started making them move. Well, that would be Newton's first law of inertia.
Okay.
And so when we go into Newton's first law of inertia, you know that as an object in motion will stay in motion until acted upon by a greater force or one of equal force to make it stop. Well, in the video, he threw it on that little bike
Spandex,
shorts,
yeah.
little spandex mat. Well, that creates friction when two surfaces touch. Well, we know that in space, it's not a whole lot of matter in space, so it's almost frictionless.
Because it's a vacuum.
Yes.
Okay. So the Earth is moving. It's an object in motion. It's going to stay in motion until acted upon by an outside force. Well, there's no friction or outside force, so the Earth is going to keep moving at the same speed and inertia until finally something comes and hits it or eats it. And I think by then we'll be in the ground anyway, so it doesn't matter.
Right.
So now we know that which objects have the greatest gravitational pull, which are the objects that are the
Biggest with more mass.
biggest or more mass. So, but is that the only thing that's doing it? Could it just be more mass?
No.
Because I have a picture here, Coach Parrish. Not drawn to scale, but we do have the sun. The sun is huge. But we also have Jupiter and Saturn. And we have Uranus and Neptune. And that little dot back there, that's Pluto. Still a planet!
It is.
But Earth is so small, and so is Mars, compared to Jupiter and Saturn. So why don't Earth gets pulled towards Jupiter and Saturn? Why is it just being affected by the sun? Why not Jupiter and Saturn?
Well, I'm going to guess they also got some type of like distance rule that they're supposed to follow too. So I'm guessing that distance has some effect on gravity.
So the planet's social distance helps with gravity.
Correct.
You know, you mentioned something earlier about magnets.
Yes.
So if I have two magnets that are far away, they really don't pull on each other, but the closer they get,
the more you feel their power.
the more you feel their power. So we get into that it's not just the size, it's also the distance that determines it. Well, that's interesting. Okay, Coach Parrish, so I have an issue. I had all these planets, and I had them all in order and all matched up based off all their facts, but my cards got mixed up. I don't know which card's which. All I know is the orbit around the sun. That's all I know for right now.
Okay.
So now we know that the objects closer to the sun have to have more gravity. They're going to be going faster than objects away from the sun. So let's start with the very first planet, Mercury. Mercury is the very first planet. It's the closest to the sun. It should have the most inertia and gravity pulling on it. So out of all these times, which one would be Mercury?
Well, if it's closer, it should take less time, so the one with the least amount of time.
And which one is that?
Well, we got years and days, and the least amount of days would be 88.
Okay, so
So
that's
that should be
Mercury.
Mercury.
Yeah. So in fact, Mercury's distance from the sun is 57.9 million kilometers. Compared to that is pretty close. So now Mercury, Venus. Now we have Venus. Venus is the second closest. So it's not going to be as fast as Mercury or have as much inertia as Mercury. So which one would be Venus?
Well, let's see. It's going to be days still, because we got 88. No. This 224.7.
Okay, and sure enough, what do we know? That's Venus. And Venus's distance is 108.2 million kilometers, almost double the distance that Mercury is from the sun. So that's number 2. So now Mercury, Venus, Earth, where America is.
Third rock from the sun.
Okay, so which one would it be? It's
Well,
still going to have some inertia, not as much as Venus. Which one is it going to be?
well, how many days are in a year?
365.
0.24, so every 4 years we have a leap year. So it's got to be that one.
Sure enough, yep, that's Earth. And the distance from the sun is 149.6 kilometers, so we're increasing almost by 50 million kilometers each time. So now, Mercury, Venus, Earth, Mars. So Mars is...
Well, we only got one more days left, so I'm going to figure this was Mars.
Yeah, and that one is Mars, and its distance is about 227.9 million kilometers. We increased by almost another 50, and that is going to be our fourth. So now we have Mercury, Venus, Earth, Mars, Jupiter. Which one is Jupiter? Now Jupiter is not going to have as much inertia as Mars, so we're looking a little bit slower. What's it going to be?
Well, now we're in years, so we got to find the slowest amount of years. So I'm going to say 11.9 years.
Okay, 11.9 Earth years, and that is Jupiter. And Jupiter's distance is 778.4 million kilometers. So here, we're increasing by 50 each time. Well, when we go from Mars to Jupiter, we increase by 500 million kilometers. And that kind of is why Jupiter really doesn't affect us. It's because it is extremely far away. Even though it's number 5, it's still 500 million kilometers away from Mars, which puts it another 700 million kilometers away from Earth. So, now we have Jupiter, now we're going to get to Saturn. And so, which one's going to be Saturn?
I'm going to say 29.5.
And it is. And so, now up here in the rock planets, we increase by 50 million kilometers each time. And here we go from Jupiter to Saturn, we're going to increase by 700 million kilometers to get from Jupiter to Saturn. So it's a big, gigantic gap. And these planets are bigger, so their gaps are bigger. And that puts us at our 6. So we have Jupiter, Saturn, Uranus.
84 years.
84 years, and yeah, that's Uranus, and it increases by another, actually this one increases by 14 million, or 1,400 million kilometers to get to Uranus. And then finally, in what science determines as actual planets, but what I don't determine, next up would be Neptune.
Or Neptune, sorry, Neptune. I forgot the end.
And then Neptune
right there
is right there, and it's 4,498.3 million kilometers, almost doubling the distance that Uranus is. So where we finally get into is as we increase our distance, so now here they are in order. My very excellent mother just served us 9 pizzas. Pluto is a planet. We are increasing our distance more and more each time. And as you can show on your side, Coach Parrish, as we increase our distance, we're increasing our...
I'm sorry, what?
As we increase our distance from the sun,
We're increasing the amount of time it takes to rotate or make a revolution around.
and decreasing our inertia. So our gravity, there's less gravity the further we move away, there's less inertia, so our time's going to increase. And so 4 main points that we've kind of really hit hard this lesson is number 1 is that gravity or gravitational force is an attraction between 2 objects interacting with each other. What's number 2, Coach Parrish?
The greater the mass, the greater the gravity or gravitational force it has.
And it's not just mass, it's also this distance. So the closer you are to something, the more gravity there's going to be. And finally,
gravity and inertia keep everything in orbit. That would be Newton's first law for the inertia for that one.
there's no friction in space. These objects are able to keep on moving and keep on moving. So with our model, what we get here is we have our sun, which is the object with the largest amount of the gravity. And the further you move away from the sun, the gravity is going to decrease. And then also, the larger the object, the more gravity it has, and the smaller the object, the smaller the amount of gravity. So this is our lesson 7, our gravity model. So lesson question, we'll go back to the beginning of the lesson. It was, why do Earth and Moon move this way? And what we figured out is, first of all, gravity is a force that attracts 2 objects or pulls them together. That objects with more mass have more gravity. Coach Parrish?
Yep. Objects that are closer together have a stronger gravitational pull on each other.
Mm-hmm.
And then gravity is what keeps the planets and moons in orbit.
With their inertia. And what was our evidence of that?
Well, that gravity video which we saw, which was really cool.
Yeah. And then also our...
Orbital period.
Yeah.
How long it takes us to go around.
So now, the question is, how did this gravity and this inertia, how did this affect how our solar system was formed? And what's really cool, if you remember back to that video, when he made the marbles go opposite directions, those marbles would collide until they were all going in the same direction.
And all of our planets are going the same direction, which means those going the opposite had to be eliminated by adding to those colliding masses.
Yeah, because they didn't just disappear, they had to go somewhere. Maybe that's how Earth got bigger and bigger, and maybe we collided with more things than Mars did. That's why Mars is smaller than Earth.
Yeah.
And you're actually doing some reading on that called How Did the Solar System Form? After you watch this video, you're going to read that. But it kind of makes me wonder, we're talking about Earth, which is a solid. Not all of it's a solid, right?
Right.
So how does gravity affect things that are other than solids?
That's a good question.
And I think we need to answer that in lesson 8. So we'll see you
Yeah.